Good afternoon, everyone. Thank you for joining us in this webinar. This event is brought to you by Institute of Advanced Studies and the Graduate Students Club of the School of Material Science and Engineering and School of Physical and Mathematical Sciences, as well as the School of Chemical Biomedical Engineering. I'm Vijay Shankar from the School of Material Science and Engineering, and I will be your host for this talk on designing confined in microenvironment at functional nanomaterial interfaces for enhanced gas-based applications. If you would like to ask questions during the Q&A session, you can use the raise hand feature at the bottom of your Zoom screen. When your name is called, you may unmute yourself and ask your questions. Alternatively, you can also post your questions in the Q&A box. Our moderators will be happy to assist you for today's session. The moderator comprises of myself, CU is from SCBE, and Arpit from SPMS. So thank you all for your kind cooperation. So I would like to take this opportunity to introduce today's distinguished speaker, Prof Lee, from School of Physical and Mathematical Sciences, Division of Chemistry and Biological Chemistry. Prof Lee's research work combines chemistry, nanotechnology, material sciences in operando spectroscopy to develop next generation catalytic ensemble to address global energy environmental crisis. He obtained both his chemistry doctorate and bachelor degree from NTU. He is also former postdoctoral scholar from Stanford University under the Singapore Teaching and Academic Research Talent Scheme. He is a recipient of NTU College of Science International Postdoctoral Scholarship, Dr. and Mrs. Alex Tan Pang Ki Gold Medal, A-Star Graduate Scholarship, and the Shell Eastern Petroleum Gold Medal cum cash award recipient. Without further ado, let's welcome Prof Lee. Thank you so much, Prof Lee, for taking time for this webinar, and I would let you take ahead through this lecture.
All right, so thank you, Vijay, for the kind introduction. So thank you again to all the GSC as well as IAS for inviting me to the IAS Discovery Science Series. So again, my name is Hiang Kwee, and I am an assistant professor at the Division of Chemistry. So the topic of my talk for today is designing confined microenvironment at functional nanomaterial interfaces for enhanced gas-based applications. So before I begin, I would like to briefly introduce myself. So let me control the Zoom a bit. All right, so I would like to briefly introduce myself. Like you, I was a student in NTU. So I obtained my Bachelor of Science in Chemistry at 2013, as well as my PhD in Chemistry in 2018. So my PhD advisor was Professor Ling Xing Yi at the Chemistry Division, as well as Dr. Pang Ying Yi, who was a scientist in A-Star. So during my PhD, I was mainly working on plasmonic materials as well as surface enhanced Raman scattering, or SERS. So after which I was awarded the NTU MOE International Postdoctoral Fellowship for me to further my postdoctoral studies at Stanford University. So the studies, the duration of this postdoc period was relatively short. So it was between 2018 to 2020, around 2 years. I was working with Professor Cui Yi. I believe those in MSc could be very familiar with him, right? He is mainly working on battery system, but instead of battery, I was working on environmental detection, battery safety, as well as catalysis in his group. Okay, so over here, this basically summarizes what I am interested in. So my research interest mainly lies in the development of novel nanoparticles, as well as hybrid nanomaterial. Understanding the fundamental science and chemistry behind these new materials via operando techniques. Right? So operando simply means that we are trying to investigate what is exactly happening on our target material as the process occurs. So after which we want to apply all this insight to address to address urgent global issues in terms of energy, environment, catalysis, and sensing. Okay. So next, before I begin, I would also like to briefly advertise on our group. So we are a relatively young group, right? So we started out around November 2020, and we only have like 6 members in the group, including me. So over the period of 1 year, we are able to expand our group to around 10 plus students and members and staff, right? So what is more important is that we are continuously trying to expand our group. And therefore, if you have, or if you are interested in a graduate studies or research staff position in our group, please feel free to email me, right, via this email over here. All right, so for this particular section, I will just be mainly focusing on one topic that I have done during my PhD studies, and this involves a material design to how can we achieve efficient gas-based processes at ambient conditions. Okay, so as a brief introduction, I would like to briefly introduce or explain the importance of gas processes in nature and industry. So in nature, we have a lot of gas-based processes. One typical and important example is photosynthesis, whereby carbon dioxide can react with water in the presence of a plant and solar energy to form glucose and oxygen. Okay, so in a reverse process, we try to oxidize the glucose form through respiration to provide us energy to sustain our body function. So in the case of respiration, oxygen will be taken by the lung, so it can react with our sugar, okay, to produce energy with the release of carbon dioxide and water as a side product. So in the case of industry, we also have many processes that involve gas, one of which is Haber-Bosch reaction, whereby we react nitrogen with hydrogen to form ammonia. As we know, ammonia is very important because this is a green fuel and this is what we use to synthesize fertilizer. Okay, so next up, we also have a magical reactions with syngas. Syngas basically means synthesis gas and involves a mixture of carbon monoxide with hydrogen. Syngas can be used for a wide variety of reactions, okay, and it involves both gas reactants. Okay, so we can use it to form hydrogen. We can use it to undergo the Fischer-Tropsch synthesis, whereby we can form long-chain alkane, those kind of value-added chemicals. But there is a great challenge to drive and monitor gas-based processes. So one of which is the low molecular concentration. So if we take a look at this bag, this is almost similar to emptiness. So this is not emptiness that we feel in our heart, so just kidding. But when I say emptiness, this is because there is a low molecular concentration inside this bag. Okay, so this bag mainly contains empty spaces in between adjacent gas molecules. Okay, so in short, even if we have a large bag of air or gas, there is only a limited amount or a small number of molecules present in this bag. So another challenge is that there is a low solubility and density of gas. So in other words, if I were to apply gas-based reactant to gas-liquid reaction, all the gas will be insoluble inside the liquid reaction medium and they will float up and escape from the liquid. So this is what we want to avoid because we want gas to interact with the liquid for subsequent gas-liquid reaction. So these two are the key challenges for us to drive and monitor gas-based reaction or processes. So what is commonly used in the industry or in general scientific community is for us to use high pressure and temperature. This is the process whereby we combine nitrogen with hydrogen to form ammonia. Okay, from this part over here, we can see that it will require very high temperature of around 450 degrees Celsius, as well as a high pressure of 300 bar. Okay, so all these elevated pressure and temperature will require an immense amount of energy for us to sustain the reaction condition. So this is what we do not want, because any energy intensive processes will tap onto the limited natural reserve that we have in our on our Earth. right? So we want to avoid using too much energy to process or to drive chemical reactions. Next, if I were to use fossil fuel, combust them to release energy, this will create a high carbon footprint whereby large amount of carbon dioxide is released to the environment. As we know, carbon dioxide is a greenhouse gas, and this can lead to global warming and climate change. So therefore, there is always a quest for us. Okay, so in this presentation, we will just be mainly focusing to answer one question. How do we drive gas-based reactions even without the need for elevated pressure and temperature? So in short, we want to avoid using a large amount of energy. And secondly, we want to avoid releasing too much greenhouse gases into the atmosphere. Okay, in this session, I will focus on a nanomaterial interface approach for us to drive efficient gas-based reaction even at 1 bar or 1 atmospheric pressure, as well as 298 Kelvin. Okay, so this approach basically or mainly utilize Metaorganic Framework as one part of a hybrid material. Therefore, I would like to briefly introduce a Metaorganic Framework so that you will get to understand what is exactly, or you will get to understand the rationale behind choosing this kind of material. So Metaorganic Framework or MOF comprises of transition matter as well as organic linker constituent. So when these two reactants are placed together, they will readily self-assemble into one unit cell of MOF and subsequently be extended to form 3D Metaorganic Framework nanoparticles. So there are two important characteristics of MOF. One is the pore aperture, the other is the pore size. Pore aperture is basically the size of our filter paper or the size of the pores on the filter paper. It will determine what kind of molecules that can pass through the pore aperture to reach the inside of the MOF material. So second, we have the pore size, which basically determines the capacity of the MOF material. So another point to note is that within the MOF material, there will be functional groups that are used to interact with the gas molecule. So this will help to absorb them within the material rather than letting them escape from this material to the exterior environment. This slide basically summarizes some of the key properties of Metaorganic Framework. So first of all, we have high specific surface area. This is required for the storage of gas molecules as well as small molecules. Next, they have tunable structural properties whereby we can change the organic linker or the metal constituent to tune its surface area as well as the pore diameter. Metaorganic Framework can also be tuned to increase their stability against high temperature as well as high volume of steam. So another key property of MOF is that they have modifiable chemical properties whereby we can post-treat the MOF material to add in new additional properties that is not initially present. So again, through the pore aperture, we are able to tune the selectivity of MOF towards certain species, so it can be used to filter out gases in air, right? So we are able to differentiate between carbon dioxide and nitrogen. So another key point, which will be the focus of this presentation, is the integration with other functional materials. We can integrate them with magnetic nanoparticles to incorporate magnetic properties into the hybrid system, as well as fluorescence or semiconductor nanomaterials. So in this section, I will basically focus on MOF encapsulated hybrid materials and their use as a selective and efficient heterogeneous catalysis or reactant. MOF are frequently used on catalytic materials, okay, like metals, to incorporate, to enhance the selectivity of this catalyst towards certain reaction. So for instance, by making use of the pore aperture, we are able to selectively filter out big molecules while only letting small reactants to enter the MOF structure and to access the embedded catalyst. So this leads to very high selectivity towards certain target reactants. Okay, so in this case, we have the yolk shell structure, okay, whereby the MOF is the shell and the catalyst is the yolk. So again, this concept utilizes the pore aperture to differentiate between big molecules and small. So only small molecules are able to penetrate through the morph material to reach the embedded catalyst. But what is more important is highlighted over here. Okay, so from this table, we can see that activation energy, which is the EA over here, is much smaller in a core shell structure compared to yolk shell, or simply palladium deposited on ZIF8 morph. Okay, so by having a lower activation energy means that my reaction kinetic will be faster, right? So this is something what we want to achieve in our catalytic system. We want to reduce activation energy. However, there is a lack of molecular level understanding of what exactly is happening at the functional solid morph interface. Okay, so what are the molecular origins behind the reduced activation energy in solid at morph platform? So that is why for my first work, I will discuss on how can we investigate the molecular events at nanomaterial interface using SIRS. So in this strategy, I embed methyl benzene thiouate grafted silver nanocube with a layer of Metaorganic Framework. So I add methyl benzene thiouate on the surface of silver so that it can serve as a molecular probe to probe the chemical environment right at the solid morph interface. Okay, so why do I choose silver nanocube? It's because of its localized surface plasmon resonance. This is very important for SIRS. Briefly, when light interact with silver nanocube, it will cause the collective oscillation of conduction band electron to create a secondary electric field. So this electric field can constructively interfere with oncoming light to further amplify the intensity of electromagnetic field very close to the plasmonic active nanostructures, which in this case is our silver nanocube. Okay, so by having a very intense electromagnetic field at the particle surface, any molecules will undergo stronger Raman scattering, and this entire process will increase Raman signal, and the process is called surface enhanced Raman scattering. Okay, one point to note is that for SIRS, it is a very surface sensitive technique whereby we are trying to probe we are trying to probe the molecular environment that is within 10 nanometer range from the particle surface. So in short, we are able to probe what exactly is happening on the particle surface. This is important for us to understand the rationale behind the reduced activation energy in core shell structure. Okay, so for our silver at ZIF platform, ZIF is zeolitic imidazolic framework. This is a type of morph that is demonstrated to have high CO2 absorption. So on this cross-sectional SEM, we can see silicon substrate over here. So all these are our silver nanocube. And what is more translucent over here is our ZIF layer. Okay, due to the polycrystalline nature of our Metaorganic Framework, we expect the formation of interfacial cavity between the silver as well as the ZIF layer. So this is due to the presence of the methyl benzene thiouate monolayer over here, as well as the polycrystallinity of our Metaorganic Framework. So again, we affirm the formation of interfacial cavity through SPS characterization. So from this SPS characterization of Ag, 3D, and sulfur 2p, we can see that there is no interaction between ZIF and silver. Okay, so this means that the morph layer or the ZIF layer is not directly in contact with the silver. So we expect interfacial cavity to be present. So again, the presence of ZIF layer over our silver nanocube is affirmed using X-ray diffraction. Okay, so this morph layer is very stable, whereby we can activate them under vacuum and high temperature of 120 degrees Celsius, and they can still be around and be stable throughout the entire reaction process. So after which we begin to in situ read out the molecular events at the interfacial cavities using surface enhanced Raman scattering. So in this example, we use in situ SIRS monitoring. Basically, we place our substrate inside a gas flow cell. So this gas flow cell got a quartz quartz light, whereby laser or Raman scatter light can freely transmit across this quartz light for detection. So from one end, we will blow in CO2, carbon dioxide gas, and the other end will be the outlet. So this is the surf spectrum that we get with continuous CO2 absorption. So initially, we started out with the characteristic surf feature of our methyl benzene thiol or MBT. So this is a CS stretching, whereas this is a CH vibrational mode. So what is more interesting is over here, whereby we can see the CO2 stretching mode of free carbon dioxide molecule. So I will go through what is free and hybrid in our subsequent slides. So as we can see, with continuous CO2 absorption or capture, there is a continuous shift and evolution of our surf spectrum with time. Okay. So the redder it is means that the intensity of this peak is higher. So if I have a blue region simply means that there is no peaks over there. Okay. So at the end of our CO2 absorption at around 105 minutes, we can see that this initially broad peak over here will get more narrow. So there is an evolution of a new surf peak over here at around 1,280. Over here in the 660 region, we can see that there is evolution of another peak around at a 660 wave number. Okay. Again, after which we try to flow our gas flow cell using nitrogen. Right. The purpose is for us to determine whether all this spectral evolution is due to physical or chemical interactions. Okay. So when we flow the gas flow cell with nitrogen, we see that there is a reverse in our spectral evolution. So simply to say, what we are observing over here will revert back to our initial state. So after purging, the surf spectrum look very similar to what we have at t equal to 1 minute. So this tells us that the change to the surf spectrum is due to physical interactions rather than chemical interactions. Okay, so next we try to flow our gas flow cell using nitrogen for the entire 105 minutes. So in short, there is no carbon dioxide, there is only nitrogen. So from this time-dependent surf spectrum, we can see that there is no change to the surf feature of our methyl benzene thiol probe. Next, we try to compare with various control platforms to affirm that the continuous CO2 absorption is the driving force behind spectral changes. So for this case, we can, in the case of ZIF, thin film, as well as the flow of carbon dioxide, we can see obvious spectral change to various parts of our spectrum. So next, if we were to flow nitrogen, but in the presence of thin film, there is not much change. Okay. So next, we try to synthesize preformed ZIF nanoparticle and deposit them onto a silver nanotube array. So in this case, we also see no changes to the surf spectrum. Last but not least, we simply use silver nanotube array in the absence of any morph nanoparticle. And in this case, we see that there is also no change. So from all these control experiments, we can see that a morph or a ZIF thin film is required to drive the spectral evolution, and CO2 is the main reason behind the spectral changes. Next, we want to unravel the molecular events at the solid morph interface. So in this case, we use DFT or density functional theory to simulate what is exactly happening to our cells as well as to our molecules. So before we do this, we have one hypothesis. That is, if we flow more CO2 into our system, there will be an increasing carbon dioxide concentration in the interfacial cavities, and this will ultimately force gas molecules towards our silver MBT surface. So in this case, without any interaction, we have an optimized intermolecular separation R around 3.75 Armstrong. So after which, from this position, we slowly let carbon dioxide molecule to approach our silver MBT surface. So this will lead to an exponential increase in the energy of the molecular system. Okay. So what is more interesting is that for the free state, whereby there is not much interaction between carbon dioxide and silver NBT, we see that carbon dioxide is a linear molecule. Okay, so upon reducing the intermolecular separation, we see that right now the carbon dioxide adopt a band configuration. Okay. Yeah, so this is mainly due to steric repulsion that caused the carbon dioxide to bend and also to elongate. This is very important because we want to identify band CO2 structure so as to confirm our theory. So subsequently, we compare our DFT simulated spectra with our experimental source spectra. Okay, what we want to confirm here is the presence of band CO2 molecule. So that is why we compare our experimental with simulation to note carbon dioxide molecule, or rather the bending vibrational mode of our carbon dioxide molecule is usually Raman inactive because they are linear. They adopt a D infinity H kind of symmetry element. That is why CO2 bending mode is usually Raman inactive. This is again indicated by our simulation, whereby we cannot see the CO2 bending mode in our simulated source spectrum. However, upon flowing CO2 gas for 60 minutes, we can see an evolution of a peak around here. So around 656 wave number. Okay, so this is the region where CO2 bending mode can be observed. Okay, so in this case, the presence of a CO2 bending mode means that our initial linear CO2 is no longer linear, right? So that is why, so in other words, this must show that a CO2 band, or rather a CO2 with a band geometry is present near our plasmonic nanoparticle surface. Okay, so using simulation, we are able to confirm this, whereby right now we are able to see the initially unobservable CO2 bending mode in our simulated source spectrum. So collectively, this comparison tells us that geometrically bent CO2 molecules are present on our, or are present near our silver nanocube surface. So one point to note is that for CO2 to adopt a band geometry, it usually requires very extreme temperature of 500 Kelvin and high pressure of 10,000 bar. Okay, so in our case, we are able to achieve this at ambient operation of 1 bar and 298 Kelvin. So therefore, our work therefore show the first linear to band carbon dioxide transformation at ambient operation. This is important because right now we are trying to create a pseudo high pressure microenvironment right at the interfacial cavity where molecules can be concentrated into a quasi-condensed phase very near to the functional solid platform like catalyst or for our silver nanocube. So after which we also compare the other source spectra or source features, and collectively we are able to induce, or we are able to infer that a pseudo high pressure microenvironment can be created in our interfacial cavity at ambient operation. Okay, so in other words, initially there is nothing inside this interfacial cavity. As we were to flow more carbon dioxide into our system, CO2 can be captured by the moth and they will accumulate in the interfacial cavity over here. So at this stage, CO2 molecule is not forced very near to the surface, and there is negligible steric repulsion, and therefore they will exist as linear geometry. But as we were to continuously concentrate CO2 molecules into the interfacial cavity, right now we are forcing carbon dioxide very near to our silver NBT surface. This will cause steric repulsion, and this will cause the formation of geometrically bent carbon dioxide molecule. So in other words, progressive carbon dioxide accumulation into a pseudo high pressure microenvironment can be seen from our result. So this is a very significant progress in the understanding of concentrating effect at solid morph interface. So usually in the scientific community, it was deemed that the gas concentrating effect is merely a confinement of gas molecule in the morph micropore very near to the solid surface. So this is not entirely true, but over in this work, we are trying to say that we are able to continuously accumulate carbon dioxide molecule into a pseudo high pressure microenvironment. So achieving this is important because we want to promote molecular concentration and energy, because this is the basis to drive chemical reaction. So right now we are able to create a pseudo high pressure microenvironment very near to the functional material surface. But are we able to use this kind of phenomenon to activate inert reactions at ambient conditions? So of course the answer is yes. That is why I'm here. All right. So before I start, I would like to briefly introduce about Kolbe-Smith or KS reaction. Okay, so this reaction involves the reaction between sodium phenoxide with carbon dioxide. So during reaction, they will adopt a 6-member ring intermediate state. Okay, they will subsequently react to form salicylic acid, whereby it involves the auto-carboxylated product. Okay, so this is auto, meta, and para. In this case, due to the formation of the 6-member ring intermediate, almost always the auto-carboxylated product is formed. In other words, the auto-carboxylated product is the most dominant product in this particular reaction. Another point to note is that for this reaction to occur, it requires high pressure of 125 degrees Celsius, as well as high pressure of 100 atmospheric pressure. So in other words, KS reaction is inert at ambient conditions. Okay, so our main aim here is to use our pseudo high pressure microenvironment to drive KS reaction even at ambient operating condition. So again, traditional KS reaction cannot occur at ambient condition, and it always forms the auto-carboxylated product. But in our design, we try to use silver surface as well as the morph layer to control the selectivity of our reaction. So in the meantime, we also want to apply our pseudo high pressure microenvironment inside the interfacial cavity to activate and drive the carboxylation reaction between our substrate with carbon dioxide to form carboxylate. So another point to note is that instead of having the auto product, right now we are able to form the meta product. So this will be discussed more in depth subsequently in our slides. So first up, let me briefly go through what is happening in our reaction system, or how to form our reaction system. So initially, we graft mercator phenol onto our silver nanocube surface. Again, this uses silver nanocube. We try to treat it with sodium hydroxide to form the phenoxide moiety. After which, we add in zinc precursor as well as 2-imidazolate precursor to form the morph layer. Okay. This is again the cross-sectional view of our platform, whereby this is silicon, silver nanocubes are over here encapsulated in the ZIF thin film. But the main point or the main highlight of this slide is that right now for our design, we are assuming that the sulfur or our substrate is attached to silver through the silver S bond, and on the other end, our oxygen atom from the phenoxide moiety is attached to the morph layer through the zinc oxide bond. Okay, so this is our key hypothesis. Are we able to affirm this? So we affirm this using XPS or X-ray photoelectron spectroscopy. So from this example, we can see that there are two types of zinc element or zinc chemical environment in our system. One is the zinc oxide. Okay. The other is zinc nitrogen. So for our system over here, we are able to see two different kind of zinc environment in our system. So this tells us that our hypothesis over here is correct. So on the other hand, if I were to use our previous configuration, whereby we graft MBT onto our silver surface, we expect no interaction between our MBT with morph, and therefore there is only zinc nitrogen chemical environment in our SPS spectrum. So affirming this is important because this insight would tell us more about what is exactly happening to cause a change in the selectivity of the reaction. So after which we perform in situ surface monitoring of the molecular changes at solid morph interface during CO2 absorption. Again, we use a gas flow cell that is made of quartz with gas inlet and outlet. So the main purpose here is to confirm the carboxylation reaction between carbon dioxide with our substrate and where is the carboxylated or where is the carboxylate group being formed. Okay, so this again is very similar to what we have seen earlier. Okay, right now the two peaks over here are the characteristic peak of our mercator phenol. What is more interesting is between the range of 1,300 and 1,400. So in this region, we expect carboxylate vibrational mode to be present over here. So as we were to flow carbon dioxide through our system, we can observe an evolution of a set of peaks very close to time equal to 60 minutes. Okay, so subsequently, as we were to flow more carbon dioxide, we see that these two peaks slowly evolve into 4 additional peaks, or rather to form 4 new peaks. Okay, so upon subsequent purging, we can see that there is a rate shift, but the peaks are still over here. Okay, so the presence of a permanent peak in the range of 1,300 to 1,400 wave number clearly tell us that chemical reactions with carbon dioxide indeed took place over here in our system. So next, we try to compare our experimental results with our DFT simulated results to unravel the molecular changes at solid morph interface during CO2 absorption. So we have a range of products that we hypothesize. Okay, so they involve auto-carboxylated product or meta-carboxylated product. So is it 1 or 2 carboxylation reaction? So we try a series of various combinations and we exclude the others and only isolate these 3 components or these 3 species out. So if we compare the experimental and the simulation data, we can see that the surf spectrum at time equal to 60 minutes correspond to this molecular configuration over here. So there is a carboxylation occurring at the meta position. So again, this is auto meta. Okay, so this tells us that there is 1 carboxylation reaction at the meta position. So after which, we at time equal to 105 minutes, we see 4 peaks in the 1,300 to 1,400 range. So this can be fitted to our simulated data of this particular spectrum, this particular molecular configuration over here. Okay, so in this case, there is a subsequent or there is a sequential carboxylation reaction also at a meta position. Okay, so through the experimental and DFT simulated results, we can see that increasing CO2 absorption will cause the carboxylation reaction at the meta position. So continuously flowing carbon dioxide or continuously absorbing carbon dioxide will subsequently drive the second carboxylation reaction also at the meta position. Okay, to highlight this is the first CO2 carboxylation reaction of arene, and they happen at ambient condition. Okay, so this is very important because right now we are able to drive inert reaction even at ambient condition. And second, we are able to rewire the selectivity of our reaction to give unconventional meta selectivity. So using SIRS and DFT alone are simply not enough because that's what always the reviewer will ask. So that is why we try to further characterize our system using XPS before and after CO2 flow. So for this case, we use C1S and O1S characterization. So in the case of C1S, before CO2 flow, we do not see any carboxylate environment over here. So only after CO2 flow for 105 minutes, we are able to see the carboxylate environment in our C1S feature. Okay, so similarly in our O1S SPS test, we are able to identify the presence of carboxylate oxygen around here in between the two peaks over here. So in short, initially it started out with only two peaks, the blue and the red. But after CO2 flow, there is an additional peak evolved, and this green peak over here correspond to our carboxylate chemical environment. So next, how do we confirm that carboxylation indeed occur at the meta position? To do this, we characterize our system using the AG3D, silver 3D SPS characterization. So upon CO2 flow, we can clearly see a red shift of the silver 3D peak, right, towards a smaller binding energy. So to understand this phenomenon, we simulate the HOMO and the LUMO. HOMO refers to highest occupied molecular orbital, right? So we investigate on the HOMO structure of our system, and from this we can see that the HOMO comprised of molecular orbital contribution from both the silver as well as the carboxylate group, right? So this tells us that electrons in the HOMO can be delocalized from our carboxylate to the silver, right? So this will ultimately lead to an increase in the electron density in our silver, and thereby leading to a red shift of our silver 3D peak towards a smaller energy, towards a smaller binding energy. So through SPS, DFT, and SURS data, we can confirm that metacarboxylation of arene indeed occur at our solid morph interface. Okay, so what is the driving force behind the activation of KS reaction even at ambient operating condition? So this again can be attributed to our pseudo high pressure microenvironment. So the presence of CO2 very close to our substrate will cause them or will force them to interact and therefore activate KS reactions even at 1 atmospheric pressure and 298 Kelvin. Okay, so in short, continuous CO2 absorption into the interfacial cavity will create a pseudo high pressure microenvironment over here. Right, so this will cause the CO2 to be bent. So if you look carefully at most of the transition state of involving CO2 molecule, they would typically involve carbon dioxide in a band geometry. So this is a way for us to activate carbon dioxide molecule. So subsequently, the reaction can flow towards the right side to form our carboxylate third product. So the origin behind, so what are the origins behind the unconventional radial selectivity at our solid at morph interface? So usually for KS reaction, they will preferentially occur at the auto position. Okay. However, with the presence of a morph coating, we are able to drive the metacarboxylation instead. Okay, so there are two possible reasons for this metacarboxylation. So this could be due to the inhibition of 6-member ring intermediate. So the coordination of the oxygen atom over here with the morph, with the zinc constituent of morph, can prevent the formation of the 6-member ring intermediate. So this could be a way for us to kill the usual auto-selectivity in a KS reaction. So secondly, the presence of carboxylate group very close to silver, right, serve as an electron sink whereby the negatively charged carboxylate group can be stabilized using the silver surface. Right. So in any case, molecules do not want to be charged and therefore they want to interact. Okay, so that is why excess electrons from the carboxylate group can be delocalized over the silver to form a more stable product. Okay, so far we have touched on reaction that involve a material surface. So can we further apply the unique properties at nanomaterial interface for emerging gas applications? So again, the answer is yes, right? So in particular, I would discuss more about the use of this nanomaterial interface to drive electrochemical nitrogen to ammonia conversion. So as a start, I would like to introduce the importance of ammonia. So ammonia is one of the highly demanded chemicals in the world. In fact, this is the second most demanded chemical in the world. Right? So this is because they have multiple purposes. One of which is that it is an efficient hydrogen source, whereby it can store hydrogen atom up to 17.6 weight%. So in other words, it serves as an efficient hydrogen storage material. So next, it is also an important nitrogen containing source for synthesis, okay, whereby we can use ammonia to interact with our organic substrate to form other kind of organic product. So next, ammonia can also be used as a green fuel, whereby we can combust ammonia in the presence of oxygen to form nitrogen and water. So in this case, there is no release of carbon dioxide, and therefore it is very green for us to use ammonia as a green fuel. So last but not least, ammonia can be used to synthesize fertilizer, which is important for our agriculture industry. So ammonia is right now regarded as the fuel of our future. Okay, so this shows that ammonia is getting more and more important in our society. And even recently, Singapore Port Authority backs project to use ammonia as marine fuel. Okay. So the use of ammonia as a fuel is important or is suitable because it has very long storage time, and it is also quite cost effective to use ammonia as a storage strategy. So typically there are two ways for us to form ammonia. So in nature, nitrogen can be converted by nitrogen fixing soil bacteria into ammonia. So the second way is for us to use the Haber-Bosch process to convert hydrogen with nitrogen into ammonia. But the key point of this reaction is that nitrogen is usually very stable, and it is very hard for us to activate the reaction. So that is why we need to have high energy input in the form of high temperature and pressure. So together, the entire scheme over here, which involves the formation of hydrogen over here, consume about 1% of the world energy consumption. So this process also emits large or massive amount of carbon dioxide, up to 200 million tons, which is about 3% of our greenhouse gas emission every year. So even consuming so much energy and releasing so much carbon dioxide into our environment, this Haber-Bosch process is only optimized at a efficiency of 10 to 15%. So in other words, most of the energy input into the system is being wasted as heat. So how do we perform, or how do we synthesize ammonia in a more sustainable manner? So one way is for us to use electrochemical reduction reaction, because this combines green solar energy with electrochemistry to convert nitrogen into useful ammonia. So there are different ways for us to perform electrochemical nitrogen reduction reaction. So this can be in the form of liquid-based electrolyte, using solid-state electrochemistry, photoelectrochemical method, which combine photocatalysis with electrochemistry, as well as our bio-inorganic hybrid materials. However, there is a very severe bottleneck in the present strategies. So if we look at the table over here, all the electrochemical system here utilize high temperature up to 500 degrees Celsius. But another key point to note is that the Ferritic efficiency is usually less than 1%. So this means that the current supply is mostly used to drive other reactions rather than our target nitrogen reduction reaction. So the efficiency is still very low, typically less than 1%. So this is due to the presence of hydrogen evolution reaction, which involve the reduction of water into hydrogen. So as we can see over here, the HER, or hydrogen evolution reaction, is represented here in the red dotted line. So over here, we have the nitrogen reduction reaction. Okay, so since HER line is always higher compared to the black line, this means that hydrogen evolution reaction is always preferred compared to nitrogen reduction reaction across most of the metal catalysts. Okay, in other words, hydrogen evolution reaction or HER basically dominates over NRR. So the question of this work is to favor nitrogen reduction reaction over HER, and are we able to perform NRR at ambient conditions? So in this work, I would tell you more about how are we able to favor the unfavored using a reticular chemistry approach. So this is a very difficult word, but it simply means the use of Metaorganic Framework. Okay, so in this case, we coat our silver gold bimetallic catalyst with a layer of MOF. So the MOF serves two purposes, one of which is to concentrate nitrogen onto our catalyst. So the second is it serves as a hydrophobic material to repel the excess of water molecule into the hybrid nanocatalyst. Okay, so by excluding water from the electrochemical system, we are able to prevent the formation of hydrogen, or we are able to inhibit the hydrogen evolution reaction. So this is what we see previously in our two works. So I will not go through them in detail again. After which we begin to characterize the reaction involved in our electrochemical system. So in this case, we use a electrochemical system whereby it involves our MOF encapsulated platform as our working electrode, platinum wire as the counter electrode, and silver chloride as our reference electrode. So nitrogen or argon are continuously pumped into our system to drive our reaction or to provide an inert atmosphere. So the electrolyte that we use is a dry THF based electrolyte, and it contains this lithium salt to conduct electricity. So 1% ethanol is added, which serves as a proton source. The other key point is that all these electrochemical reactions occur at ambient conditions at 1 atm and 298 Kelvin. So firstly, we compare the electrochemical performance or the CV, cyclic voltammetry performance for both of our platform. One involves MOF encapsulated catalyst, the other does not involve MOF encapsulated catalyst. So in this case, for the argon case, we note an oxidation peak over here. Okay, so this is related to ethanol oxidation reaction. So after which, during the reverse scan, we see that there is no reductive peak in this region. However, in the presence of nitrogen bubbling, we also observe the anodic peak over here. But there is also an occurrence or emergence of a new nitrogen reduction peak over here at negative 2.6, around negative 2.5 volt. Okay, so if we were to compare these two cyclic voltammogram, we can see that this peak over here is very obvious, and it only occurs when nitrogen is bubbled into the system. So in another way, we infer that this peak, this reduction peak, could be due to nitrogen reduction reaction. Okay, so in contrast, in the absence of any MOF coating, we see that the cyclic voltammogram are similar whether we bubble nitrogen or argon inside the system. Okay, so we also observe an anodic peak that is related to ethanol oxidation reaction. So furthermore, we also observe two water electrolysis peaks at around this position, negative 1.8 volt, as well as around negative 2.8 volt. Okay, so I will go them in detail later to explain why do we identify this peak to be related to certain species. So next, we also perform the same as Raman, but right now, instead of using a thin film layer, we preform these 8 nanoparticles and deposit them onto our bimetallic catalyst. Over here, we can see that they are rather porous, right? So in another way, water can still penetrate through this thick layer over here to access the electrocatalyst at the bottom. That is why we are still able to observe water electrolysis peak over here for our this system over here. Okay. Yeah. So in our thin film configuration, we can exclude water, the excess of water efficiently, and there is no presence of water electrolysis peak around negative 1.8 volt and negative 2.8 volt. However, when we deposit these nanoparticles onto our bimetallic catalyst, we can still see the presence of water electrolysis peak at negative 1.8 and negative 2.8 volt. So this again tells us that complete encapsulation of hydrophobic ZIF across the entire bimetallic catalyst is necessary. So we further identify the electrochemical features using various control experiments. So if we were to spike our electrolyte with 20% water, we observe an increase in the magnitude of the reduction current. Okay, so the onset is very similar to the onset of the water electrolysis peak over here. And of course, we are able to see bubbles being formed, and this tells us that the reaction related to this peak is again attributed to hydrogen evolution reaction. So next, to affirm that the anodic peak over here is indeed indexed to ethanol oxidation, we also perform one control experiment, but in the absence of any ethanol spike into the electrolyte. So from this example, from the blue dotted line, we see the absence of the anodic oxidation peak, okay, and also the absence of a reduction NRR peak. So this tells us that this peak over here is indeed due to ethanol oxidation. And the second point is that ethanol is important as a proton source for our NRR reaction. So we subsequently confirm the electrochemical reduction of nitrogen into ammonia by quantifying the amount of ammonium present in our system. So we do this using the indophenol blue method, whereby we convert ammonia into ammonium and subsequently into indophenol blue, which is a blue dye. So after which we can quantify the ammonium present by quantifying the characteristic peak of indophenol blue at around 640 nanometer. So this is the calibration curve that we can use to quantify the amount of ammonium present. So next, by quantifying the amount of ammonium present, we are able to determine two important figures of merit. One of which is Ferritic efficiency. Okay, so this is basically the percentage of electron supply to the system that can be used to create ammonia. So the higher it is, of course, the better the electrochemical system is. So second, we have the rate of ammonia generation. So from this table, we are able to see that the rate of ammonia formation is relatively similar compared to what is in the literature. But what is more important is that simply by coating hydrophobic MOF on our bimetallic system, we are able to increase Ferritic efficiency by at least 10 percentage point. So although 10 percentage point may seems like a small number, but this is in fact very significant. Again, because most of the Ferritic efficiency in the scientific community is very low and less than 1%. Okay, so this less than 1% efficiency is also observed when we were to use very high temperature. So in other words, we are able to amplify the Ferritic efficiency by 10 percentage points simply by coating a MOF layer across our electrocatalyst. So this again occur at ambient condition without the need of elevated temperature or pressure. So this is the mechanism of our study, whereby nitrogen can be absorbed into our hydrophobic MOF and subsequently react with electron and ethanol to form ammonia. So this ammonia can be dissolved from our system and subsequently characterized or quantified using the indophenol blue method. So for the MOF, it also serves as a hydrophobic barrier, whereby it prevents the access of water to our embedded electrocatalyst. So if water cannot access, then we will be effectively inhibiting the hydrogen evolution reaction. Okay, we can also affirm that the interfacial cavity or the pseudo high pressure microenvironment can be used to enhance electrochemical nitrogen reduction performance. So over here, we hypothesize that nitrogen can be continuously accumulated in the interfacial cavity, and this will facilitate subsequent electrochemical reduction. So from the cyclic voltammogram observed, we are able to note that the reduction potential of the cathodic peak will shift towards a more positive voltage. So by shifting to a more positive voltage means that it is relatively easier for nitrogen reduction to take place. So this is good because we want to reduce the overpotential that we use for our electrochemical reduction reaction. So another point to note is that through the continuous accumulation of nitrogen in our interfacial cavity, we can provide a ready supply of nitrogen to our electrochemical surface, to our electrocatalytic surface. So that is why we are able to sustain our peak current even when we were to cycle the electrocatalyst for many cycles. Okay, so in short, if I am able to sustain the magnitude of our peak current, this means that nitrogen reduction reaction can be sustained over a long period of time. Our design is also robust, whereby we do not see any hydrogen evolution peak even after 100 cycles. Right, so this tells us that our design is very stable, even under electrochemical conditions, right? And they are still efficient to exclude water from our system even after many cycles. So I guess we are already at a 1 hour mark, so I will briefly just go through these 2 slides, all right? So by further employing the insights that we have gained from our previous study, we can further utilize all these designs to create plasmonic nodes to smell volatile organic compounds at the molecular level. So in this case, again, we combine plasmonic nanoparticles with MOF. Like we want to pre-concentrate them or pre-concentrate the analyte molecules on the SURF active platform. So this will create very sensitive plasmonic nodes, whereby we can use it to smell volatile organic compound like toluene vapor to quantify them, as well as to reuse them. So the other important application is to drive or to concentrate immiscible gas liquid molecules as solid MOF interface for reaction monitoring. So in this case, our gas reactant is carbon dioxide, liquid reactant is aniline. So we want to concentrate them right at the interface. So by concentrating them, we are forcing them to interact and therefore subsequently drive their reaction. So one key point about this design is that the MOF should also exclude solvent molecules from the system. Else, solvent molecules are usually present in high concentration. And if solvent molecule can access the MOF, then most of this interfacial cavity will be occupied by the solvent molecules. This is again what we do not want in our system. We just want the gas and liquid molecules to be present over here. Okay, so through SURF monitoring, we are able to confirm the formation of carbamide through the reaction of aniline and carbon dioxide. So all this process again occur at 298 Kelvin and 1 atm. So another point to note is that this reaction cannot occur at ambient conditions. So again, elevated temperature and pressure is required. So the second point to note is that this carbamide species over here is very not stable, it's very unstable. So far there is no way for us to extract or to isolate this product out for SC2 characterization. Okay, therefore this comparison tells us the importance or emphasize the importance for in situ monitoring of reaction, especially when it involves a very unstable product or intermediate. So with this, I would like to conclude my presentation. Sorry that this could be slightly long, right? So I hope that I am able to convince you that we have created a pseudo high pressure microenvironment at a solid MOF interface. So this pseudo high pressure microenvironment is very useful and can be further utilized to activate chemical reactions and also to enable gas reaction monitoring without the use of elevated pressure or temperature. Okay, so usually for gas monitoring, we will want to pressurize the system because this will allow easier detection. But right now, even at ambient condition, we are able to achieve both of these scientific achievements, right? So by further incorporating different functions of the morph material, we can also design unique electrocatalytic design to achieve efficient and selective gas to chemical transformation. So ultimately, I hope that through this presentation, I'm able to inspire you to employ this kind of unique phenomenon and extend to other functional materials to create new opportunities. So with this, I would like to thank, all right, so for this, right, most of the work presented here were done during my PhD studies. So therefore, I want to thank or acknowledge the support from my PhD advisors, Prof Ling as well as Dr. Pang, as well as our collaborator, Professor Frank Chong. So he has passed away due to COVID. So it's very, yeah, okay. So last but not least, I would like to thank my group mates or colleagues who have helped out in these experiments. So again, this will not be possible without the funding support from NTU as well as STAR. So if you are interested to know more about what I have done during my PhD postdoctoral studies, and more importantly, what I'm doing now, you can feel free to email me via my email or to visit our website. So with this is the end of end of my talk. So thank you for your time and attention. Yeah, thank you.
Thank you, Prof Lee, for introducing us to such an interesting topic and your research area as well. I believe this is very pertinent to sustainable gas-based applications. So I think a lot of us who are actually interested in this area, definitely we should get to know more about it. And I especially would love to contact you after this because I have something in line with this. So thank you, Prof Lee. So now,
thank you. Yeah.
So now let us move on to the interview session with questions from MSc as well as SCB, and also we have questions from the audience as well. So I'll move on to the question session.
Okay, sure.
So Prof, one of the important questions that a lot of us in MSc, in fact, through our discussions and brainstorming, we came across, and we wanted to ask you this: that can this technology be used to remove or treat the targeted regions like corrosion on metal surfaces?
Okay, so I would say that are we able to use morph, coat it onto rust, and try to use gas to reduce them back to iron?
Yes, you're right.
Okay, so I guess most of the rust are formed in our environment. Okay, so if we were to coat them onto our rust, there is no oxidant present that can be used, or there is no reducing gas present that can be used to reduce rust into their initial form. Okay, so unless you are doing them in a very confined environment, right? So I don't think this idea may work, right? But it's still very hard to say unless we are able to continuously introduce hydrogen into the system and try to force hydrogen to reduce the rust into the iron. Okay.
So Prof Lee, so actually there is an extension to this question. So let's say that if it is very difficult in terms of removing the rust, how about creating an accelerated corrosive area in a particular metal interface? Is that possible?
Sorry, again?
What about accelerated chemical reaction to develop corrosion in the metal interface? Can that be possible with the use of MOF and the in situ, the microenvironment that you're talking about?
So you're trying to say, are we able to coat morph onto steel and try to make them corrode?
Yes, yes.
I think it will be possible, right? So, but again, this will be done within a confined environment. So are we able to use this in open air is still a question. Yeah, so of course, in open air, we need to have oxygen. So it may be possible if our moth is able to selectively concentrate oxygen and water onto the steel surface.
Oh, okay, Prof. Prof,
Yeah.
moving on to the next question. Could you please give us more insights into some of the technical challenges that you had faced during your project, during the PhD, and even in your current research? So what are the key takeaways from such challenges that you had faced?
Okay, so for the first case, right, the data that we got that time were mainly SIRS as well as DFT simulation. So, however, this is an indirect way for us to indicate or to denote the presence of interfacial cavity. Okay, so this is one important technical challenge because we are not able to image out what is exactly forming at this interface. Okay, so in short, this interfacial cavity is still not yet visualized or confirmed using electron microscopy and so on. Okay, so for the second case, this involves a surface type of reaction. Okay, but so far we are not able to isolate. Okay, so we have DFT simulation, we have SIRS, we have SPS. Okay, but we are not able to isolate out the product for further characterization. So as a rule of thumb in research, we want to have as many characterization methods as possible so that this will add credibility to our research. Right? But in fact, this is a quite a technical challenge for this particular second project. Yeah. So for the third case, I would say it's pretty okay. Yeah, but one aspect is already highlighted by one of the questions in the group, in the chat box. So typically MOF or Metaorganic Framework can be unstable in solvent solution. Okay, so how are we able to extend the insight that we gather over here in solid MOF interface or solid MOF system into other more stable porous material? Right, so are we able to integrate our concepts over here with covalent organic framework, which is more stable, and get the same stuff again? Yeah, so I think fundamentally being able to visualize the formation of this interfacial cavity could be very important for us to affirm all these mechanisms. Yeah.
So, Prof, moving on, I would also like to ask something more on the project basis. Like, besides the monetary aspects, what are the other roadblocks or the hurdles you see with this technology to mature and be translatable to a larger scale? I mean, could you please add your thoughts on how to deal with situations where you see a barrage of problems that can potentially topple the future of the project?
Okay, so one key problem that I see from the three works over here are stability. Okay, what we do are very in a very controlled environment. So we are doing all this experiment in a very controlled environment. Okay, but MOF or Metaorganic Framework is known to be unstable under certain conditions. So are we able to overcome these challenges could be critical for us to translate all these fundamental insights into real application. Okay, so that is why are we able to expand the insights gained from the three experiments or the three work to other kind of porous material that is more stable, could be a determining factor to whether our technology can be translated into practical applications. Okay, so for the second part, I have a bit forgotten that what you have asked.
Yeah,
so
sure.
Yeah, sorry.
Definitely. Could you? I wanted to ask you, like, could you please add your thoughts on how to deal with, situations where you see a barrage of problems that can potentially literally topple the future of the project. Sometimes when you hit a roadblocks in your project, and then you literally see there is no way ahead in that situation. Like, how do you deal? I mean, how do you foresee dealing with such situations, or have you dealt with such situations in the past?
Okay, so usually the first thing to do is do not cry. Okay, so this is very common in research. Okay, do not cry. Try to have a calm mind. Okay, so after which I would say, even before you start your experiment or your project, try to think of possible failures that you can encounter. Okay, in this case, you will not be that shocked by all the failures. Okay, so at any time, right, in the case that you foresee any failures, right, try to think of 1 to 2 backup and do it simultaneously. Okay, so for research, most of the time we fail. But what keeps us going is that we do not say, we just keep on going. So we don't say that this is the end of the project. Yeah. So you got to have a very strong heart. Yes.
I understand. Prof, I would like to conclude my questions and then I'll pass on to see you. So this is actually a very pertinent question because this is something related to the collaboration aspect. In 2019 review paper, Present and Future of the Surface Enhanced Raman Scattering, it's quite unusual to see the amount of content and the huge, around 60 authors, 50 laboratories and 90 pages and almost 1,000 references. Could you please tell us about the logistics behind this kind of cooperation work and the challenges that were involved in it?
Okay, so for this part, right, I must admit that I'm not the first author. So I'm in fact not really behind the logistics, but this is in fact very impressive for the first author and the corresponding author. So for that case, right, they invited all the top experts in the field. Right, they sent invitation to whether are we going to participate in the paper writing. Okay, so after which we will propose something that we want to write about the topic, about SIRS. So after which the first author will organize all the points together and make them into a smooth flow. Then we started to write our content. Okay, yeah, so the work done by the first author is really impressive because there are 60 authors and most of them are writing on different parts and they are very in-depth. So yeah, so that's why I'm not really sure about the logistics, but I think this is a very impressive collaboration between all the international experts in the field. Yeah.
Prof, now we go ahead with few questions.
Okay, sure.
Okay. Hi. Thank you, Prof, for the very informative research. I have personally done with the MOF myself in my FYP project back in China. But starting from here, I would just ask some non-technical question, and I would continue with the Q&A section, whereby some people ask some very specific technical question. Sure. So from my side, I was just wondering, because nowadays a lot of students are not sure whether they will go to, a lot of PhD students not sure whether they will go to academia or industry. So for you, do you always know that you want to be a professor someday? And what would be the biggest factor that persuade you to go for academia?
Okay, so to the first part of the question, I do not have idea that I will become a professor. Okay, so why do I choose academia or PhD studies over industry? Is because I like to solve questions. Right? I like to solve challenges. So in research, there are a lot of questions that are unknown to most people in the world. So I find that this could be challenging for me to take up, and that is why I'm interested in research as well as PhD studies. Okay, so after which I was offered the opportunity. So in fact, I was offered 2 opportunities, one to a research institute, the other to NTU. Okay, so at that point of time, I have trouble confirming which to choose, but ultimately it is harder for me to know what I want, but it is easier for me to know what I do not want. Yeah, so that is why I do not like routine stuff. I do not like to have someone above me who keep nagging at me. So I would like to have the freedom to do what I want to do. So that is why I choose academia over industry again. Yeah, so for those who are thinking about what to do with life, especially for undergrad students, just apply for the scholarship as well as the industrial application, all right? Then when you see what you have, you will have a clearer mind to what you can choose. Yeah.
Okay, second question. If you have to name one, what would be the most important transferable skill that you have obtained during your PhD? Yeah.
I think the most important skill is skin hardening. Okay, so skin hardening basically means that you will need to have a very thick skin, all right? So if you have trouble with some research, try to ask for help. So we have questions on scientific concept, try to ask a lot. Okay, so there will be a lot of failure, but those are very common in research. So you have to have a really big heart and thick skin for you to accept all these. Okay, but sometimes failures can lead to opportunities. So don't be disheartened by failures. Try to look at what is exactly happening and can we use failure to derive something that is more interesting and unexpected. Yeah, so skin hardening could be very important.
Okay, thank you, Prof.
Yeah.
That's inspiring. Okay, we can now move on to the Q&A section. And I see some students have asked. So a student named Pan Yao asked, thank you so much for this wonderful talk. We've learned a lot about how implanting MOF in gas-related chemistry. I wanted to ask if you have any question on how we can determine the regioselective of the KS reaction beyond DFT or XPS.
This is a very good point. So just now I was talking about we do not have the ability to isolate this product out. Okay, so another point to note is that even if we can isolate this product out, will the isolation process change the product again to another more stable form? So right now in this process, silver could be important. Silver can be important to stabilize the meta position carboxylate. Okay, so that is why right now we are mainly focusing on surface sensitive technique for us to identify the presence of unconventional selectivity. But are we able to isolate this out without changing the product being formed at the initial state? Is still a very big question. And so if you have any idea, please let me know. So if not, I would say surface sensitive method could still be the best at the moment.
Okay. I hope that answered the student's question. Then we'll move on to the next question asked by Kevin.
Okay.
He asked, do you see any limits to the scalability of MOF-based reactors? And second, what is limiting?
Okay, so about the scalability of this kind of platform, so I would say MOF is already commercialized. Okay, we can of course make use of all this commercialized platform or MOF platform to impenetrate or to impregnate our catalyst or functional materials right inside the pores of this MOF material. Okay, so I do not see any problem in scaling up. So there are a lot of methods like wet synthesis and mechanosynthesis. Okay, but the key question is how stable is the hybrid MOF-based hybrid material is still a very big question in the field, right? So if we cannot solve this stability issue, there is no point for us to scale up at the moment. Yeah, so there is different aspects of MOF research, and some of us are working on MOF stability issues, and the other are working on hybrid nanomaterials. So collectively, I hope that we are able to be a scientific community that try to solve all these issues, right? And try to translate more technology into something useful. Yeah.
I see during our registration, Kevin also asked questions. The question is, so they are investigating the hydrolysis of PET polymer in textile. Would you have a cost-effective way of catalyzing this reaction at 1 atm and 298 Kelvin? Thank you.
Yeah, so for this question, I must admit I am not an expert in polymer chemistry, but what I'm seeing in the polymer structure is that there is a lot of carboxylate kind of moiety in the polymer. So what we can do could be possibly coating this kind of polymer with a layer of moss and try to concentrate water and the other kind of oxidant or reductant into the moss and into the interfacial cavity formed between the polymer and the moss. So hopefully these pseudo high pressure microenvironments are able to drive the degradation of the polymeric material even at ambient conditions. So I do not have actual concrete plan, right? So many of these are still hypotheses. Whether can we achieve this or not still need experimental confirmation.
Thank you, Prof.
Yeah.
I don't know if there's any students still want to ask question. If so, you can raise your hand to directly ask the question. If not,
maybe I will just add on one more question.
Okay.
Yeah, but see, Prof, what is the link between surface enhanced Raman scattering and interfaces for enhanced gas-based reaction?
Okay, so for this case, let me go back to our slide. Yeah, for this case, from this particular example, we can see that for core shell structure, it experiences a lower activation energy compared to, right? But we are not exactly sure what is happening at the space between the morph layer and the functional nanoparticles. Okay, so that is why we want to use SIRS to let us know the molecular event that can occur at a chemical environment very close to the functional platform. So in other words, we want to be able to determine what is actually occurring within the space over here. This is something that bulk characterization cannot achieve. Okay, so we want to make use of SIRS to understand what is exactly happening at the interfacial cavity. So SIRS again can give us information about the vibrational fingerprint, and which can be used to tell us more about the molecular structure and how molecules can interact with one another. So through this example, we can see that instead of mere confinement of gas in morph micropores near the solid surface, we are in fact able to accumulate CO2 inside the interfacial cavity to form a pseudo high pressure microenvironment. So this is something that is not expected in the scientific community. And through this, we are able to expand it into different kind of applications. So I would say that SIRS could be the linking point behind the fundamental science with potential future practical applications. So we want to understand more in order for us to apply something more efficiently. Yeah. I hope I answer your point. We cannot hear you.
Yes, Prof. Sorry.
Yeah.
You actually further elaborated it, so it was quite good, Prof. Prof,
Yeah.
May I just ask one more, and then that probably I can end it with that.
Sure.
Yeah. So in the current nitrogen fixation has a massive impact in the agro industry and human-induced pollutions. Your approach could basically revolutionize the field. However, agro industry's production volume is so huge that the active interface area needed would be tremendous. how to upscale to be competitive and how to manufacture these nanoscale devices for active interfaces at industrial level.
Okay, so for this part, I would say that the first question is about the scale of the synthesis. Okay, so most of the methods that are presented here does not or do not aim to replace the Haber-Bosch process, but rather we want to, but rather we want to give an alternative sustainable approach for us to create ammonia in a more sustainable manner. Okay, so as long as we are able to cut the cost of all this electricity as well as to achieve better Ferritic efficiency, right now the synthesis of ammonia using electrochemistry method could be somewhat similar to the Haber-Bosch process. So of course, this cannot be produced in a volume that is comparable to Haber-Bosch process in the near future. But right now we are trying to cut out. So we want to produce or provide alternative ways so that we can reduce the extent of use for our Haber-Bosch process and try to replace it with, or try to substitute it with a more sustainable method. So in general, this will be like a hybrid kind of system, whereby most of us are still using HB reaction, but some of us are trying to produce ammonia in a more sustainable manner. So this is very similar to our hybrid car. Okay, we want to use electricity, but we also want to tap on the advantage of using diesel or those kind of oils. Yeah, so you can, I don't think it can replace Haber-Bosch process totally very soon, but we aim to reduce the extent that we use Haber-Bosch process.
Oh, certainly, it seems like this research is sowing the seeds for the future of industrializing such processes.
Sorry again.
And this research of yours is certainly sowing the seed for the future of industrialization of such processes. I mean, in future, probably we may see that how we can industrialize such small nanoscale processes to large scale processes.
Yes, yes. This will certainly require time. Yeah.
So basically, we can say that this is a TRL, technology readiness level of 3 to 4, and it needs to go to, you're approaching higher TRL levels in the future.
Yes, this is still very upstream research. So right now, the main focus is still for us to achieve high Ferritic efficiency at the moment. Okay. So if the process cannot be efficient, then the Haber-Bosch process could still be the best manufacturing method at the moment. Yeah.
So Prof, I would like to thank you from behalf of all the graduate student club fraternity and IAS for taking time and joining us for today's webinar. And I would like to thank all of the participants who have participated in this webinar. And before everyone leaves, please do scan the QR code for the survey as well as for the attendance. We value your feedback to help us improve our future webinars as well. So thank you very much.
Thank you.
Thank you, Prof.
Yeah.
Thank you. Bye.
Thank you. Bye.